Okay, welcome everybody. It's my great pleasure to introduce today's speaker, Professor Michael Demkowicz from Texas A&M, and this is lecture number 6 of the CREDDS Summer School. This is titled Basic Mechanisms of Slip. Mike got his PhD from MIT, working with Professor Ali Argon. Graduated in 2005, then he joined Los Alamos National Lab as a director's postdoctoral fellow. He became a staff member there. Then he moved to MIT as assistant professor, and he's now at Texas A&M as associate professor. He has done well there. He is a residential impact fellow, and of course we all know him as the director of the CREDDS Center. His research interests are broad-based in metallic materials and extreme environments using a range of modeling and experimental techniques. So with that, very pleased to introduce speaker today, and Mike, take it away.
Thank you very much. So before we get started, one thing that I wanted to do is just ask everybody if you would be willing to unmute your cameras so we can take a group photo. The idea here, and anybody who's willing to do it, please do it. If you're not willing to do it, you don't have to do it. But for whoever is willing to do it, it would be nice to have a little photo for our for the CREDDS website, just so we can advertise how many people are actually participating. So if you're okay with it, I'm going to give you just a minute to unmute your camera, and then we can remute again, and we'll proceed with the lecture. All right, so far I've got a couple of takers, but not a whole lot. Getting better. I'm going to stop as soon as we get to full screen.
You can try again next week. People can come prepared.
Anybody? People are in their pajamas. Is that it? Maybe that's the problem. Okay, maybe there's like a smaller version. No. Okay. All right. Maybe we'll try again next week. At some point, I wanted to get a nice little group photo here of us, but maybe next week is this will do if we're in a pinch. But otherwise, we'll just do it next week. Okay. Well, thank you very much. Thank you for those of you who are willing to do it. Okay. So let's fire up the presentation here. All right. So today I wanted to spend a little bit of time telling you about the basic mechanisms of slip. And I realize that for many of you, this is going to be a review. But I think that it makes sense to get on the same page about some of these basic issues, especially as later on you'll be hearing a lot more about how this stuff plays into plasticity behind the shock front, the occurrence of slip bands during flow localization and things like that. So I wanted to spend a little bit of time just getting on the same page about these basic mechanisms of slip. Now, when we talk about basic mechanisms of slip, and of course I'm talking here in the context of crystalline materials, we're talking about dislocations. So I won't go into the history of dislocations and dislocation mechanics, how dislocations came about. Instead, I will simply state that at this time, dislocations are well known, they're well established, they are easily imaged. So here I'm showing you a picture taken from a book called Introduction to Dislocations by Hull and Bacon. A very good introductory book to dislocations if you're looking for one. And on the left-hand side, you see a TEM image of a foil, a metal foil containing dislocations. Each one of these dark lines that you see here is a dislocation segment. right? So each one of those is a dislocation segment, and then over there in the sort of in the back, you see another array of dislocation segments. Each of those dark lines is a segment. Each of the segments sort of has a starting point and an ending point. And the reason why you have these start points and end points is because you're looking at a thin foil, and so the dislocations are coming out from one surface and going over to the other surface. Right, so this is just a sort of 3D illustration of the 2G projection that you see in TEM. Here's another TEM image of dislocations. This is in gamma titanium aluminum, an intermetallic material, taken a little bit more recently. So the sharpness is a little bit better. The imaging conditions here are a little bit better than the previous image. But the bottom line here, the thing that I'm really trying to sort of convey here is that the existence of dislocations, our ability to interrogate them experimentally, none of this is in question anymore. Right? So this is a core fundamental area of material science, and it's acknowledged to be really the underlying physics responsible for deformation in most crystalline materials. Some of them involve twinning as well, as Irene Bayerlein will tell you in the next lecture. Okay, so dislocations are defects in crystals. They are line defects. They're one-dimensional defects, right, as opposed to point defects like vacancies or interstitials, which are considered zero-dimensional. They're just points in space. Dislocations have length, right? So they're not point defects because they have length. They're not area defects because they have no area, right? So they're not like grain boundaries or surfaces. They only have length, not area. So they're line defects. And so if you want to describe a line defect, a dislocation, you need two quantities. Okay, so one of them is the line direction. So this C hat that I'm showing you here, this Greek letter C with a little hat over it, is a unit vector. The C hat is defined, by the way, just so it's clear, this sort of squiggle here, the black line, is a dislocation. Right? I've just drawn in a random dislocation. At any point along that line, I can draw a tangent vector, and the tangent vector is the line direction. Okay, so at any point I can define a line direction. Now, when we define line directions, the definition is arbitrary, right? So I can define the line direction as pointing this way, or I can define it as pointing the opposite way. The only constraint is that it must be defined tangent to the line of the dislocation, right? So it's always tangent. And of course, when we define line directions, we tend to define it in such a way so that if you're going along the dislocation, let's say from this point to this point, right? If I sort of pass along this dislocation, I want the direction of the line direction vector C never to change, right? So I don't want the definition changing from one point to the other. I want it always to be pointing in the same direction. So that's how we define Xi. Just to emphasize, Xi is not a constant, right? It as the shape of the dislocation is not a constant in general. Dislocations can be curved. Therefore, Xi can be pointing in different directions. It's not a constant, all right? The other quantity that you need to define a dislocation is Berger's vector. And two important differences between the line direction and the Berger's vector. Line direction is defined as a unit vector, right? Because here we're interested in just the direction, right? Xi only tells you about the tangent direction. There's no interest in assigning a length or magnitude to it. So it's a unit vector. That's why it has the hat. The Berger's vector has a length, right? It's not a unit vector. It has units of length. And so, you usually see Berger's vectors expressed in angstroms or in nanometers. So that's one difference. The other difference is that once the line direction is specified, once you actually provide the line direction of the dislocation, the Berger's vector is fixed. And it's fixed by a process that I'll tell you about in just a second. Of course, you all know it probably. It's the Berger circuit. But it's not arbitrary, right? Line direction, I can define pointing any direction I want, as long as it's tangent to the line. Berger's vector, once I have the line direction, is given. And furthermore, Berger's vector, being a topological quantity, a topological property of the dislocation, is constant. So as I go along this entire length of this dislocation, the Burgers vector is never changing length or direction, right? So it's the same here as it is here, as it is here, even though the line directions are changing, all right? So those are the two things that you need to define a dislocation: line direction and Burgers vector. So how do you define the Burgers vector? Well, so you've probably all already heard about the Burgers circuit, but I just wanted to make sure, I think that a lot of times this is taught in a relatively qualitative way, but it's important to be quantitative about this if you want to use your knowledge about dislocations in a quantitative way. So let me just walk you through the convention that is used for defining Burgers vectors in a little bit more detail. So on the left, what I'm showing you here is a schematic arrangement of atoms containing a dislocation. Right? So this is a crystal. In fact, it's a simple cubic crystal. Simple cubic crystals are very rare, but they're also very simple. So they're often used to illustrate things like dislocations. And what I'm showing you here is an edge dislocation core, right? So this upside down T illustrates an edge dislocation. And this edge dislocation corresponds to the termination line of an extra plane of atoms. So you see there's a plane of atoms that goes down like this. There's a plane of atoms that goes down like this. There's another one that goes down like this. And there's 3 planes of atoms on this side. Here I have a plane of atoms that goes down a certain distance and then stops. It terminates. That terminating edge is an edge dislocation, right? And I'll be a little bit more specific on what exactly that means. But the important thing is that when you look at this configuration, you realize I'm talking about a line, right? The dislocation is not the extra half plane, right? The dislocation is the edge of the extra half plane. The dislocation is also not an atom along that edge. It is the entire edge, right? So you should think of this edge dislocation as running into the plane of the screen here, and it is a line that runs along that entire length. Now, now that I've sort of clarified that what I'm talking about here is a line, I'm going to abstract away from the 3D view, and I'm going to stick with a one-dimensional view. Sorry, two-dimensional view. Okay, so I've gone from this 3D picture to this 2D picture. Okay, and in this 2D picture, I am going to draw what's known as a Burgers circuit. Now, before we go on to draw the Burgers circuit, it is important to keep in mind the line direction. Okay, and this is something that may have been omitted to you when you were first introduced to Burgers circuits. This dislocation in 3D is a line, and so the line, and the way that I've drawn it, the line is going perpendicularly into the board. And so which ways can the line direction point? Well, I know it has to be tangent to the line of the dislocation. So the line direction, C hat, that I defined for you before, has to be going either perpendicularly into the board or perpendicularly out of the board. One of those two options. Which one you choose is arbitrary. It's up to you. However, it's important that you choose one, okay? And the reason why it's important that you choose one is that when you are going to draw your Burgers circuit, you have to follow a convention, and the convention is known as the finish to start right-handed convention. The right-handed part, and my video is on, so you should be able to see me. I'm going to show you my right hand, right? You all have worked with the right-hand rule in physics, right? So the right-hand rule is going to be important for you when you're drawing Burgers vectors as well. When you use the right-hand rule to draw a Burgers vector, you take your thumb and you point it in the direction of the line direction of the dislocation. So I'm just going to assume, I'm going to make the arbitrary choice that the line direction of this dislocation is pointing into the screen, right? So it's going to point from where I'm looking to where you're sitting, right? That way. And when I want to draw a Burgers vector, I take my thumb and I point it in that direction. Okay, so I'm pointing my thumb towards you, towards my screen. And then I curl my fingers of my right hand, and that curl of my fingers tells you the direction that the circuit needs to go, right? So once you know the the line direction of your dislocation, that tells you which way you have to draw your circuit. You may not draw it the other way, you know, or if you do, you'll be wrong, right? You'll get the wrong value. Okay, so it's important that you point your thumb into the along the line direction, and then the curl of your fingers tells you the direction of the Berger circuit. So as you can see in this image that I'm showing you here, the circuit is basically just a path, a closed path that encircles the dislocation, and it goes, in this case, clockwise, because I've assumed that the line direction points into the board, and so if I use my right hand to draw the circuit, it has to be a clockwise circuit, right? So there it is. Now, important, when you do the Berger's vector, when you do the Berger's circuit construction, you must always draw this closed circuit in the configuration that contains a dislocation, right? So whatever configuration you're trying to investigate and construct the Berger circuit in, or find the Berger's vector of, you always construct this closed circuit in the configuration that you think contains the dislocation, right? The next thing you do is you go to a reference configuration that you know does not have a dislocation. So this is just going to be a perfect crystal, okay? This perfect crystal is, of course, hypothetical, right? I mean, it's just something that you draw out on a piece of paper yourself, but it's important that it's the perfect crystal. And then you redraw this circuit that you drew over here, you redraw it over here, right? So again, if this is a crystal, of course, it doesn't matter where you start, right? So I can choose any of these atoms as my starting point, okay? But here the starting point is selected to be this atom. And then I draw the circuit by counting the number of nearest neighbor distances along each segment in this configuration on the left. So, 1, 2, 3, 4 segments of nearest neighbor distances going up, 1, 2, 3, 4 going to the right, then 1, 2, 3, 4 going down, and 1, 2, 3 going to the left. Okay, so I do the same thing here. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. Right on the bottom part, I just had 3. Okay, and now you see that in this reference configuration, in this reference state, the circuit no longer closes, right? So here you finished where you started. Here you do not finish where you started. There's a difference between the starting and the finishing point, and that's known as a closure failure. Now, your Berger's vector is the vector that closes the circuit, right? So it's that extra little bit of distance that is needed to close that circuit, to mend up that closure failure, okay? And the other important part of the convention that we're dealing with here is that when you define your Berger's circuit, you must always go finish to start, okay? So the Berger's circuit ends here at the point labeled F, and here's the starting point. So my Berger's vector is defined as going from here, F, to here, S, okay? Finish to start. You have to observe these conventions, right? If you want to have a Berger's vector, if you want to come up with a Berger's vector that will allow you to use all the machinery of dislocation mechanics, you have to use this convention. If you reverse your definition of the line direction, right? So if I were to say my line direction of this dislocation is not going to be pointing into the board, but out of the board, then that reverses the direction of the circuit on the left. Rather than having a circuit that goes clockwise, I have a circuit that goes counterclockwise. And so then when I draw that circuit on the right-hand side, my finish and my start locations are going to be switched, right? So if I were to reverse the line direction, my finish would be here and my start would be there, okay? So I would get a Berger's vector from that, which has the same length as before, but now reversed direction. Right, so this is why it's important for you to keep track of your line direction. Depending on how you define your line direction, that will determine the sign of your Berger's vector. Okay, so the Berger's vector is fully defined once you choose the line direction, but the sign of the Berger's vector does depend on the choice that you make for the dislocation line direction. Okay, so these things are important to do. I just wanted to also mention one other thing. the reason why we draw the Berger circuit on the left in the configuration with the dislocation, and then redraw it again on the right in the reference configuration with no dislocation, and the reason why we define the Berger's vector on the right and not on the left is because you can see that the crystal lattice in this configuration on the left is strained, right? You can see that it's got a lot of distortion in it, and that's because the dislocation is a defect. It's got a strain field around it. All of the sort of atomic bonds and interatomic distances around the dislocation, especially near the core, are strained. Okay, so if I were to define my Berger's vector here on the left rather than on the right, then the value of the Berger's vector, definitely its length and possibly its direction as well, would depend on how I drew the circuit, right? If I have the closure failure occurring, I don't know, here, I might get a different answer for my Berger's vector than if I had the closure failure occurring here. So if I draw this circuit, if I define the Berger's vector on the left, then it depends on how I draw the circuit. But if I define the vector on the right in the reference configuration, well, all interatomic distances here are identical. And so no matter how I draw the circuit, I'm always going to get the same outcome. I'm always going to get the same answer for the Berger's vector. So these, conventions that I'm telling you about here are important, right? It's because it's basically thanks to these conventions that you can be quantitative about your Berger's vector, and it's thanks to these conventions that you can assure that the Berger's vector is actually independent of the way you draw the circuit. I just wanted to, briefly just mention when I lecture in class, I usually encourage people to ask questions. There's, I think, 40 or 50 of us right now on the chat. I think that's not so much that if there's a question of clarification that somebody wants to ask, you should unmute yourself and ask me. I'm happy with that. If you have like sort of a more detailed, in-depth question, that's going to involve a lot of discussion, maybe hold off on that. But if you have sort of immediate questions on the way that I'm defining this or why I'm defining things one way or another, I definitely do stop me because it might be easier to just get those things resolved now. Okay, this circuit that I drew for you here is for an edge dislocation, and an edge dislocation is this sort of terminating point of an extra half plane, as I already told you. The thing that defines once I know a Berger's vector in the line direction, the thing that sort of formally defines what an edge dislocation is that the Berger's vector is perpendicular to the line direction. Right, so the line direction here is going into the board, right? It's going perpendicular to the board, and as you can see, the Berger's vector is horizontal, right? This is the direction of the Berger's vector. So the line direction and the Berger's vector are perpendicular. There's a 90-degree angle between them, and whenever you have that whenever that happens, right? Whenever the line direction and the Berger's vector are perpendicular, that's what makes an edge dislocation, right? That's the definition of an edge dislocation. There's also, as I think most of you know, screw dislocations. And screw dislocations occur when the Berger's vector and the line direction are parallel, right? So when a Berger's vector and the line direction are parallel to each other, that's a screw dislocation. Here I'm showing you the construction of a Berger circuit involving a screw dislocation. So this is a 3D drawing of a crystal structure that has a screw dislocation here. This is the core of the screw dislocation. And you draw a circuit, right, a closed circuit as you would before you have to define a line direction. So in this case, the line direction is moving sort of into the board diagonally, right? I know that it has to be because I know that the right-hand rule has to work. So I can point my thumb along the line direction, and then the clockwise, sense of the circuit tells me that the line direction has to, which way the line direction has to be. And then I take this same circuit and I redraw it in a reference crystal with no dislocation. And in this case, the closure failure is an interatomic distance that passes perpendicular to this, face to this plane of atoms that you see facing you, right? So this Berger's vector here is parallel to the line direction, which goes sort of into the board like that. And that's what makes this a screw dislocation. So, when the Burgers vector is parallel to the line direction, that's screw. When it's perpendicular, that's edge. But of course, dislocation line directions can be pointing in any direction, right? So screw dislocations and edge dislocations are really sort of isolated points in the space of all possible dislocation types. Anytime that you have a line direction that is not parallel or perpendicular to the Burgers vector, that's a mixed dislocation. And of course, most dislocations are mixed. So this is another sort of image showing you a dislocation in a crystalline structure. The way that this picture was drawn is that you have two planes of atoms, one on top of the other. And you're looking down on those two planes. So all the white circles are atoms in a plane that is on the bottom, and all the black dots are atoms that are in a plane that are on the top, right? So the black things are on the top, the white things are on the bottom, and you can see that there are regions where the black and the white coincide, so that's a perfect crystal region. And then there's this sort of gash going down the middle where the black and the white don't coincide. That is a dislocation, okay? As you can see, it's a line defect, right? It's got length, all right? And you can see that the direction, the line orientation, the line direction of this dislocation changes from being like this, right? And in between, it's something in between, like that. And so that tells you that this picture that I'm drawing for you here has to contain a segment that is edge, a segment that is screw, and a segment that is mixed, okay? And one of your homework problems that I wanted to give you for today is to take this drawing and do an actual Burgers circuit construction at different locations along this drawing, and confirm that the Burgers vector is the same at all locations, and B, figure out which locations on this figure are edge, which ones are screw, and which ones are mixed. Right? And I'll come back to that. I'll restate the homework problem again in a second. Okay.
There is a request in the chat.
Yes. Yes.
Can you please replace your pointer with laser pointer, if possible?
Okay, let's do that. How can I do that? How do I do that? Does anybody know how to do that? Maybe laser pointer. Laser pointer. Like that?
Yeah, looks good.
Okay, good. Excellent. All right, so we'll do the laser pointer. Okay. So I've told you the two important quantities, the Burgers vector and the line direction. Once you know the Burgers vector and the line direction of a dislocation, you can calculate, you can obtain from that an important quantity known as the slip plane, okay? And in this picture that I was showing you before, which contains an edge dislocation running along this edge of this extra half plane, right? In this picture that I showed you before, the slip plane is going into the board, and what I'm showing you here is an edge-on view of the slip plane. Okay, so this dashed line that you see, the red dashed line going here, is a slip plane. Okay, it goes into the board, and this vector n hat is the normal vector that's perpendicular to the slip plane. How do you describe planes mathematically? You describe them with the unit normal vectors to the planes. So n hat tells you the orientation of the slip plane. Now, and you can calculate it, right? So once I know the Burgers vector and the line direction, I can calculate the slip plane, right? So in this case, it's just the cross product of the two. And then the bottom part here is just a normalizing factor, right? It's ensuring that n hat is a unit vector, right? So I'm normalizing. But basically, you just take the cross product. And you know that the line direction here is going into the board. The Burgers vector is horizontal, and so the cross product is going to be vertical, right? You know that from the properties of cross products. Slip planes are very important because they distinguish between two types of motion that dislocations can undergo: non-conservative motion and conservative motion. So what's the difference between the two? Non-conservative motion is the kind of motion that requires mass to be transported to the dislocation or away from the dislocation. Non-conservative motion, whenever you have non-conservative motion, the mass transport that is required is generally accommodated by diffusion, right? So diffusion in most crystalline solids occurs by vacancy migration, right? So if a dislocation is undergoing non-conservative motion, the rate at which it can move is limited by the diffusivity of vacancies, typically. Okay, so if I'm looking at this edge dislocation and I want this edge dislocation to move upward, well, the way that I have to do that is I have to remove this stack of atoms. Right? So I'm using my laser pointer here to indicate for you a stack of atoms. That whole stack of atoms has to be removed for this edge dislocation to move upward by 1 interatomic spacing. Okay, how are these atoms going to be removed? Well, they're going to have to diffuse away. Right? They're going to have to undergo self-diffusion, vacancy-mediated self-diffusion to diffuse away. Similarly, if I wanted to move for this dislocation to move downward by 1 atomic dimension, I would have to move in an extra row of atoms. How are those atoms going to move? Again, by diffusion. All right. So for the dislocation to move perpendicular to the slip plane, normal to the slip plane, I have to add atoms or remove atoms. That is a process that's slow because it is limited by diffusion. Okay, that process is called climb. On the other hand, if I want to move the dislocation parallel to the slip plane, that does not require mass transport. I do not have to wait for atoms to arrive at or get transported away from the dislocation core. And because mass transport is not involved, glide can be quite fast, right? So unlike climb, which is limited by the rate of diffusion, my thermally activated process, a relatively slow process, glide occurs very fast, or can occur very fast, right? So knowing what the slip plane is very important. Now, some of you might sort of look at this expression here and immediately notice, well, this is all well and good for edge dislocations, where the Burgers vector and the line direction are perpendicular. It's also fine for mixed dislocations, where the Burgers vector and the line direction are not parallel. They might not be perpendicular, but they're not parallel, okay? But if I have a Burgers vector that is parallel to the line direction, well, that's a screw dislocation, right? And if I have a screw dislocation and those two vectors are parallel to each other, their cross product is going to be 0, okay? And what does that mean? Does that mean that screw dislocations don't have slip planes? The answer to that is depends on how you look at it, right? So from the perspective of sort of pure theoretical dislocation mechanics, the answer is that's correct. Screw dislocations are not confined to one single slip plane. Screw dislocations can undergo what is known as cross slip. They can move along one slip plane and then move along some other slip plane that's oriented differently. They can undergo cross slip. So that's from sort of the purely theoretical standpoint. In practice, the kinds of planes on which dislocations can easily move depend on the crystal structure and on the element that you're looking at, right? So in any given material, the planes on which dislocations are likely to slip, to glide, the planes on which slip is likely to occur, is determined by the crystallographic structure of those planes, right? So in reality, even a screw dislocation, which is not sort of confined to one single slip plane by this equation on the bottom, is going to have a certain finite set of slip planes to choose from. Okay, so if now that we know the idea of a Burgers vector and a slip plane, we are able to define something that's known as a slip system, right? So a slip system is basically a combination of a slip plane and a slip direction. Slip direction is a Burgers vector direction. This table that I'm showing you here has been taken from the book by Ali Argon, Strengthening Mechanisms in Crystal Plasticity. It's basically a compendium of slip systems in different materials. So what you have here on the top are slip systems for a bunch of face-centered cubic materials, FCC, metals, and intermetallics. And in face-centered cubic materials, the slip planes tend to be 111 planes. The 111 planes in face-centered cubic materials are the closest packed planes. They are the planes on which dislocations can move the most easily. And the slip directions, which are also the Burgers vector directions, are the 110 type directions. So slip systems are all the possible combinations of the distinct slip planes and slip directions. Okay, so every sort of combination of slip planes and slip directions is what's known as a slip system. One sort of caveat that I wanted to mention here. According to this equation that I just showed you, right, this one right here, the Burgers vector and the slip plane cannot be chosen completely independently of each other, right? As you can see, the slip plane actually depends on the Burgers vector, right? So there are many different line directions that a dislocation can take, but once you've determined the Burgers vector, the number of slip planes that it can change, that it can assume is limited, right? And basically it's limited to planes that actually contain this Burgers vector. Right? So the Burgers vector, this Burgers vector must actually be contained in this slip plane. And that's quite easy when you don't have a when you have a when you're not dealing with a screw dislocation, right? When you're dealing with a screw dislocation, there's just one possible value for the slip plane. When you're dealing with a screw dislocation, the slip planes that are available are all the slip planes that contain the Burgers vector of the screw dislocation, right? So not slip planes that are somehow oblique towards the Burgers vector of the screw dislocation. They have to actually contain the Burgers vector of the screw dislocation. Okay, so slip systems are combinations of slip planes as well as slip directions that are contained within the slip plane, right? So if I were to look at any particular plane in a FCC crystal, for example, let's say I look at the 111 plane, well, there are three possible slip directions, right? There's 1 bar 1 0, there's 1 0 bar 1, and then there's 0, and then there's 0 bar 1 1. So those three slip directions are actually contained within a 111 slip plane. A 110 direction is not contained within the 111 plane, right? So I can't have a slip system that has a 111 plane and a 110 direction because, as I already said, the slip direction has to be actually contained within the slip plane. So going further, you can see that there's the situation gets more complex as you sort of go up in complexity in the crystal structure. Aluminum is an interesting FCC metal because it has a fair degree of directional bonding. It has a fair degree of covalent bonding, and so that results in slip along 100 type planes being possible as well. Alpha iron is sort of a prototypical BCC metal. Of course, the thing that distinguishes it from many other BCC metals is that it's magnetic. But as you can see, it has a number of different slip planes. The slip direction is always the same, the 111 type slip direction, but slip planes can be a variety of different planes. Other BCC metals such as molybdenum, niobium, tantalum, tungsten, chrome, vanadium have the same two slip planes that alpha iron has, but they don't seem to show this 1, 2, 3 slip plane as much. And then HCP metals have a variety of different active slip systems depending on the difficulty of forming stacking faults on different planes within HCP crystal structures. I'm not going to go into that in any depth because you're going to get a full dose of HCP crystal structures in a week when Irene Byerline does her presentation. So once I know the slip system, what can I do with that? So let's move on. Once I know the slip system, I can compute the plastic strain that comes about from a dislocation moving. To give you an idea of how dislocation motion gives rise to plastic strain, I'm just going to do a very sort of simple schematic sort of diagram to motivate this formula here on the bottom, and then I'm going to give you sort of a more general formula to describe the plastic strains that arise from dislocation motion. So suppose that I have a cube, and here I'm showing you just the XY face of that cube. So here's my coordinate system. So X, y, and z is coming out of the board. So think of this as a cube where the z direction is coming out of the board. Okay, I'm looking just, orthogonally perpendicular to one of the faces of that cube. And in the initial state that I'm going to consider, this, cube is undeformed, is just a perfect cube. If I now have a dislocation, an edge dislocation that moves through this cube, cuts across a plane that moves through the sort of center, let's say the center line of this cube, right? So if I have a dislocation that moves through the center line of this cube, it's going to shift, it's going to shear that cube such that the bottom half is still where it is, but the top half has been translated over to the right by one Burger's vector, right? So this is the outcome of one dislocation gliding from left to right along a plane that moves through that's located at the center of this cube. Okay. As a result, I have a step that forms on the right surface as well as on the left surface. The magnitude of that step, the size of that step, is equal to the Burger's vector of the dislocation. What if I wanted to take this configuration on the right and describe that change in shape that has occurred as a homogeneous uniform strain? Well, for starters, I'm making an approximation, right? You can see that this shape on the right has not been strained uniformly compared to the shape on the left. The top hasn't been shifted with respect to the bottom, so there's a step. It's not a uniform strain, but I'm going to approximate it as if it were a uniform strain, and that's what these dashed lines are supposed to indicate. So if I were to approximate this shape on the right as having been uniformly strained, then I can think of it as having sort of skewed over to the right, like a deck of cards, undergoing what we know from mechanics as simple shear, right? So going from left to right, the dislocation has imparted a simple shear to this configuration once I sort of average over these steps and wash out the steps. And what is the value of the pure shear? If I wanted to sort of compute for myself the pure shear that has occurred as a result of this deformation process, well, I can write it like this, right? So this is basically just one strain component. Strain, of course, is a tensor. It has 6 independent components. The P here is to indicate that it's a plastic strain. XY is the component that I'm talking about here. If I wanted to compute the simple shear, I will just take this Burger's vector magnitude and divide it by the length of this cube in the y direction, L sub y, right? So that's how I would compute a simple shear. I would take this amount by which the cube has been sheared over, which is equal to the Burger's vector, and divide it by Ly. That gives me the simple shear. If I wanted to figure out what is the pure shear, of course, simple shear contains a shear and a rotation. From the tensorial perspective on strain, it contains both a shear and a rotation. So if we want to take the rotation out, then we're interested in the pure shear. And to relate a simple shear to a pure shear, all I have to do is divide it by 2. Right? So this is just sort of basic mechanics stuff. If I want to take the rotation component out, I just divide it by 2. So this B over Ly times 2 is the pure shear that has occurred as a result of the dislocation moving across this cube. Okay. Now I'm just going to do a couple of manipulations, very simple manipulations to lead me closer in the direction of the formula that I want to arrive at. I'm going to multiply both the top and the bottom part of this formula by Lz, which is the dimension of the cube going out of the board, and Lx, which is the dimension of the cube going horizontally. Okay, and of course, to keep the equality, I have to multiply the denominator by Lx and Lz as well, right? So I'm allowed to do that. I can multiply the numerator and the denominator by the same quantity anytime I like, right? So I'm just going to do that. If I do that, you can notice that the denominator, this Lx times Ly times Lz, is nothing more than the volume of the cube, right? The top, Lx times Lz, is the area swept by the dislocation as it moves across this cube. Right? So sometimes you'll see this plastic strain arising from a dislocation written as 1/2 of the Burger's vector times the area swept by the dislocation divided by the volume in which this is occurring. Okay? I'm going to write it a little bit differently. I'm not going to write it that way. Instead, what I'm going to do is I'm going to observe that the length of the dislocation, if I have a dislocation, whose line direction is perpendicular to the board, and the dislocation is moving from left to right, I'm going to observe that the length of that dislocation is L sub z, right? That dislocation has the length of the cube going out of the board, right? Because that's the orientation of the dislocation, right? So L sub z is the length of the dislocation. And then, as I already said, Lx, Ly, Lz, that product is just the volume. So if I take the length of the dislocation divided by the volume, I get what's known as a dislocation density, rho, right? And in the literature on dislocation mechanics, you'll often see this quantity rho showing up. You can think of rho as being analogous to, whenever you learn kinetics, for instance, presumably you learn about, for example, vacancy concentrations, right? Constant vacancy concentrations are number of vacancies per unit volume, right? So that's the vacancy concentration. Rho, you can think of rho as being analogous to a vacancy concentration, except you're not measuring the number of vacancies per unit volume, you're measuring the number of dislocations per unit volume. Now here you have to sort of keep in mind that vacancies are zero-dimensional defects. They have no length or area, nothing like that. Dislocations are line defects, so they do have length. They don't have area, but they have length. And so if you want to figure out the concentration of dislocations, you have to write that down not as a number per unit volume, but as a length per unit volume, right? So this dislocation density is always going to be written as a length per unit volume. Right? Similarly, if you wanted to figure out the amount of yarn that you have stored in your closet, you might write it down as the volume of your closet, as the length, total length of yarn divided by the volume of your closet. Right? So that's kind of what a dislocation density is. It's the length per unit volume. All right. And so if I adopt this value rho, then I can rewrite this expression for the strain as 1/2 times the Burger's vector times rho, the dislocation density, times Lx. And what's Lx? Lx is the distance that the dislocation has moved, okay? So in this example, I have the dislocation moving across the entire length of this cube. So Lx is just the dislocation displacement, if you will, okay? All right. So, and you can see that this formula comes from very simple logic, right? There's nothing magical or sort of mysterious or unusual about where this formula comes from. It's just simple accounting. It's nothing more than accounting. Okay, so now we're going to take this formula one step further, and I'm going to write it in this form. Okay, now I know it sounds like a big step going from here to here, but it's actually not a very big step at all, right? Really, I've only done two things. First of all, I've made this formula incremental. So whereas here I have a strain related to a total displacement, here I just have an increment of strain related to an increment of displacement dx, right? I think that shouldn't raise any eyebrows, right? So I can think of the displacement as being some infinitesimal displacement, and in that case, I just get an infinitesimal strain, all right? Here, I talked about a specific component of strain, the xy component, just because of the way that I set up this example. But here, I've replaced x and y by I and j, which is basically just to say that the expression that I'm giving you here is general. It holds not just for the xy component of strain, but for any of the 6 independent components of strain, right? So I can figure out the strain component, any strain component of the plastic strain coming from the dislocation using this formula, all right? B and rho, the Burger's vector and the dislocation density, that's unchanged, right? That's still the same as it was before. Nothing has changed there. And the only additional thing that I've introduced here is this thing here called alpha ij, right? And I'll come to that in a minute, exactly what that means. For now, just note that it's a constant, right? It's not something that depends on the Burger's vector or rho or anything else. And the value that alpha ij takes in this example that I showed you here is just 1/2, right? So in this example that I had here, it's just equal to 1/2. And here it's something else, alpha ij. And now I see that I have a typo. Okay, so I'm sorry, there's a typo in here. It's a very simple typo, so I'm just going to exit the slideshow and fix it rather than propagate it. Okay, you'll see in a minute why I did this. My apologies. Okay, just to sort of, you know, this equation really is a really simple equation, raises no eyebrows. You know, hopefully you're all fine with it. Okay, I am going to take this equation and divide both sides by dt, infinitesimal increment of time. Okay, so if I divide both sides by dt, then I get d epsilon ijp divided by dt. And what is that? Well, that's just strain rate, right? So that's the strain rate. And then on the right-hand side, I get dx divided by dt. Okay, so what's dx by dt? Velocity, dislocation velocity. So, so basically what I have here is an expression that relates strain rate to dislocation density, dislocation velocity, and this thing alpha ij. Okay, now what is alpha ij? Alpha ij is known as the Schmidt tensor. Okay, so Schmidt tensor is a tensor, right? So it is a rank 2 tensor. That's why it has 2 indices, right? So this is a formula for the components of that tensor. So I can take on values from 1 to 3. J can take on values from 1 to 3. This whole thing can be written as a matrix, obviously, and I don't know why I lost my laser pointer. Let's bring back the laser pointer. Okay. This alpha ij can be computed if you know the components of the slip plane, which is given by the normal vector n hat, and if you know the Burgers vector, right? So if I know all the components of the Burgers vector is a vector in 3D, so it's got 3 components. The slip plane is given by the normal unit normal vector. It also has 3 components. So if I wanted to compute any value of alpha ij, I just, you know, plug in the components of the normal of the unit vectors here. Okay. Now, in this particular example, I was considering an edge dislocation, right, going from left to right. So in the case of an edge dislocation, this is really simple. I know that there's going to be, you know, if I'm looking at a slip plane, which is aligned entirely with the y direction, right, so that I'm going to get one non-zero value of n, right, that's the y component, and the Burgers vector that's going to contribute to that is just the Burgers vector along the x direction, since this is an edge dislocation. So this whole thing is going to, you know, turn out to be 1 times the Burgers vector times 1/2, right? So that's why on this expression here I get 1/2 the Burgers vector, right? But again, I think the value of having this tensorial expression is that now you're not limited to just that one geometry that I showed you on the previous slide. You can now compute this a relationship between the strain rate and the dislocation velocity for a Burgers vector and slip plane oriented in any way that you like, right? So for any orientation of the slip plane and the Burgers vector, it's super, super easy to compute this, okay? And this is known as the Schmidt tensor, okay? By the way, I think that a lot of you are familiar with the idea of a Schmidt factor, right? And Schmidt factors are basically just, you know, these prefactors that occur, you know, when you compute the Schmidt tensor. So you know, Schmidt factors are sort of easier for people to get, you know, to get their introduction to dislocations when, you know, before they've had to deal with tensors. But I think that, you know, since you're all adults, you can deal with tensors. You can leave the Schmidt factors behind, and you can just deal with Schmidt tensors. It's much, much easier. It's 100 times easier, trust me, to deal with the tensors than it is to deal with the factors. Okay, once I have an expression for the strain rate, I can compute the rate of work, of plastic work done under a certain applied stress. Okay, so if I have a certain applied stress, and of course you all know that that if I stupid same similar sort of typo occurred there. My apologies. Okay, if I wanted to compute the rate of plastic work done, all I have to do is take the tensor contraction of the stress that's acting on the material, on the volume of material I'm interested in, and contract it with the strain rate tensor. So I am, of course, assuming Einstein's notation here. Einstein notation means that whenever you have repeated indices, a sum over those indices is implied, right? So here I have sigma ij, epsilon dot ij. The I is repeated, right? There's an I here and an I there. That means that there is implied in here a sum over I, okay? The J is also repeated, so there's implied a sum over J, right? So there's a sum over I and J that occurs here, okay? This whole expression can be rewritten as this thing on the right, okay? Tau, quantity called tau, Berger's vector B, rho, the dislocation density, V, the dislocation velocity. Tau B, the product of this quantity tau and the Berger's vector, is just this tensor contraction between sigma, the applied stress, and alpha ij, which is the Schmidt tensor. Okay? This tau is known as the resolved shear stress. That's the component of the shear stress. That's the component of the stress that's been applied to the material that actually does work when the dislocation moves. Okay? And you know that you can write this down as just a single component because just a scalar component, right? Rather than, stress tensor has 6 independent components, but we can boil down that stress tensor to just one single resolved shear stress scalar, that's acting on a dislocation, because when we're computing the work rate, we're actually taking this tensor contraction between the stress and the strain rate. Right, so these two tensors get contracted together, and what's left is a scalar, and it's very convenient to think about just this resolved shear stress acting on a dislocation rather than all the 6 sort of multi-component 6 independent components of stress acting on a dislocation. Right? This is a great convenience. Okay, now that we've gone through and defined for ourselves the important quantities, we're now in a good position to talk about what governs the rate at which dislocations can move. And let me actually just let me draw your attention to this expression here for just a second, right? So here's, before I move on to the next slide, this is an expression for the strain rate. And once again, I lost my laser pointer. This is an expression for the strain rate, okay? And this is telling you that the strain rate is equal to the product, well, of alpha ij times the dislocation density times the dislocation velocity, right? So if you start from a material that is at 0 strain rate, and you suddenly apply to it a high strain rate, this expression is telling you that there are 2 ways that that strain rate can be accommodated. Either the dislocation velocity increases or the dislocation density increases, right? And both of those ways can give you an increase in the strain rate. So because the sort of the applied strain rate can be accommodated in these 2 distinct ways, figuring out experimentally which one of them is actually operative is actually rather challenging. Figuring out whether your strain rate is being accommodated by an increase in dislocation density or an increase in dislocation velocity is hard, okay? So it took a full, I would say, 4 decades since the idea of dislocations were first posited to the time when people first were able to measure, the dependence of dislocation velocity on the resolved shear stress, okay? So let me talk a little bit about dislocation velocity first, and later on I'll talk a little bit about dislocation density and how dislocation density can change. So this is a picture. This is a figure that's taken from a classic picture by Follansbee, Cox, and Regazzoni. Now, Regazzoni is the only one of those that I don't know, but Cox and Follansbee are sort of staples in the field. So if you read through the literature here, you'll see those names recurring a lot. And in fact, this paper that I'm referencing here was actually used by Amit in his lecture from last week, right? So he was showing you the dependence of stress on strain rate, and that picture also came from the same paper. But this figure here is showing you is a plot of the mean dislocation velocity, right? So velocity as a function of stress, and specifically we're talking here about the resolved shear stress, right? So this tau that I was showing you here before, this stress on the bottom here is the resolved shear stress. So that combination of stress components that actually does work on the dislocation as it moves, as it glides, right? As it moves within its slip plane, right? So all of this is related to slip and not to climb. So there are a couple of sort of regions in this plot that I think it's important to talk about. You know, if you want to understand the things that govern dislocation velocity. And the first one is the one here, right? So first of all, you can see that the dislocation up to a certain stress in this plot is shown as not moving at all, right? So in this plot, until you get up to a certain stress, the dislocation has zero velocity. Once you hit a certain stress, the velocity takes off, right? And it takes off rather steeply, right? So, and then, you know, after a little while, it begins to flatten out again and becomes, you know, more or less proportional to the applied resolved shear stress. And then it begins to flatten out again and asymptote to V sub s, which is the longitude, which is the transverse wave speed. It's the shear velocity, right? So a couple of lectures ago, you were introduced to the idea that if you were to take the shear modulus of the material divided by its density and then take the square root of that, you would get the shear velocity, shear wave speed. And here you're seeing that, you know, as you move up to higher and higher resolved stresses, the dislocation velocity tends to sort of asymptote to this shear wave speed, right? And it doesn't, at least experimentally, as far as I know, you know, so there are atomistic simulations that have been done that suggest that sometimes dislocations can actually jump above the shear velocity, but I'm not aware of any experiments that actually show dislocations moving faster than the shear wave speed. Okay, so we have to talk a little bit about what makes for these different areas in this plot, and to help out with that, I put together some lecture notes. Okay, so I am going to go through some of those lecture notes, and I'm also going to send those lecture notes out to you once, you know, along with these slides. But before I do that, I guess let me just talk about this one other thing. I mentioned that it took a long time from the discovery of dislocations to the first measurement of dislocation velocity as a function of shear stress. The first example of such a measurement was conducted by Johnston and Gilman. Okay, and this is a classic paper from 1959. They had a rather ingenious, you know, approach. They conducted these experiments on lithium fluoride. Lithium fluoride is a compound, right? It's not a pure element. It's a compound, and it's a compound that is susceptible to being etched. And so what you see here is a figure that I've taken from that paper. This was published in 1959, so they were rather lax about their scale bars, I see, at that point. So this figure has no scale bar. But what you see here is a little sort of diamond, right? And that diamond is actually a conical pit. Right? So if you take lithium fluoride, you submerge it into acid, that acid is going to eat away at the surface of the lithium fluoride, and wherever a dislocation comes out onto the surface, wherever you have a dislocation emerging onto the surface, the acid is going to eat away a little bit more strongly, right? It's going to etch a little bit deeper at that location than in other places. And so every time you see one of these little conical pits, that's telling you there's a dislocation core that's coming out onto the surface there, okay? And so what Johnston and Gilman did, and to be more precise, Gilman was the professor and Johnston was the grad student. So what Johnston had to do for 5 years for his PhD thesis was to etch these surfaces of lithium fluoride, okay, to get a pit, then he would apply a very, very short burst of loading, right? So he would apply load to up to a certain controlled value of stress and then immediately take it off. Okay, so just a very, very small short burst of loading. And then, and of course they would try to figure out, the time that the load was applied. And then they would take that same sample and etch it again. Okay, and as a result, they would get etch pits with two different sizes, right? You see there's a small etch pit and a big etch pit, right? One of these etch pits is big because that's where the dislocation was at the beginning, right? So this area actually got etched twice, right? It got etched at the beginning when the dislocation was here, and then it got etched again, and of course the pit was already there, and so it etched a little deeper because it was sort of like this, imperfect depression in the surface, which tends to etch a little more. And then you had these other regions where you had the smaller pits, right? And the smaller pits are telling you where the dislocation ended up. Okay, so as a result of this, they knew that the dislocation started here and ended there. They knew the amount of time that they applied the load, and they knew what the load was, so they could figure out the velocity, and they could plot it as a function of the load. And this is the plot that they got, right? So this is dislocation velocity as a function of applied shear stress. And they were able to fit a sort of phenomenological expression to this, right? So there's nothing really like fundamental or mechanistic about it. They just fit a power law expression, and this is a power law expression of this form. Tau zero is basically some critical value that you have to attain before you can get any motion at all, right? So you can think of that as a critical resolved shear stress, CRSS, as they wrote here, right? Resolved shear stress is that tau value that I was telling you about before. And n is an exponent, that in the work of Johnson and Gilman, they found that it could be between 10 and 20, right? So it's relatively steep. But this kind of study was repeated many times, right? So there are many other people who repeated this kind of study. And, so you can imagine that there were, probably dozens of PhD theses, that were put together in this way using a similar technique. And this sort of phenomenological expression seems to hold relatively well, okay? And by the way, you can see here that this, the power law, this is a log-log plot. I hope you've all noticed this is, spanning many, many decades of velocity over a relatively, small region of applied critical resolved shear stresses here on the bottom. This is a log-log plot. This power law fit applies to this section here that appears approximately linear. Okay, so this is the relatively low resolved shear stress region, and then as you get to higher and higher resolved shear stresses, you can see that this trend begins to turn over, and indeed you get to see that it seems to sort of turn over as you're getting closer and closer to the shear wave speed, right, which is this dashed line up here. Okay, so experimentally, that's how people have sort of experimentally determined dislocation velocities. It's a relatively tedious process, but it seems to work rather well. Okay, so let me talk a little bit now about. I'm going to jump now to my notes that I told you I would show you, and I'll give you these notes as well. So I'm going to jump to my this screen. So hopefully you can all see my this PowerPoint thing. So I prepared about a dozen pages of notes about dislocation motion, and this contains some of the basic information that I've told you already about the orientation of slip planes. It says a little bit about slip systems in different crystal structures. There's a little bit of extra info there if you want it, but very, very shortly after that, it proceeds on to this section about glide, and I see that I have the same typo here that I need to resolve. So I'll do that in a minute. Okay. But in the meantime, I wanted to use these notes to talk through some of the reasons why you get different regimes in the behavior of in the behavior of dislocations, and the velocity of dislocations as a function of applied stress, using the notes that I've written in here. Okay, so just by by way of reminder, this is in relation to this plot that I was showing you before, right? So you should all have in your mind this plot, which shows these series of transitions between different kinds of velocity behaviors as a function of the resolved stress. Okay, and I'm going to talk through some of these things. So first, I'm going to talk about this sort of cutoff that you see here. Then I'm going to talk about this rising part in the velocity, this rapidly rising part in the velocity, which, by the way, I guess it's important to point out, this part right here, it's labeled here as thermal activation with drag. This part is highly temperature dependent, right? So the dislocation velocities along this section depend on temperature very, very strongly. And the reason why they depend strongly on temperature is because they're thermally activated, right? The velocity here depends on thermally activated processes. Beyond a certain value, which here is labeled as tau hat, the velocity becomes essentially independent of temperature, right? Which is basically telling us that beyond a certain resolved shear stress, the processes that are responsible for dislocation velocity are no longer thermally activated. They're activated entirely by mechanical force and not by temperature, not by thermal agitation. And then eventually you get something here called relativistic effects. And yes, it's sort of like Einstein's theory of relativity, but in the case of dislocations, and I'll talk about that as well. Okay, so let me now jump back to my notes here. Here we go, my notes, and I think you can hear my lovely children there in the background. So I might have actually skipped one extra slide that I should have gone over first. Yes, I did. So let me go back to my slideshow one more time. I apologize for the back and forth. So I said that I would start out by telling you about the origin of this sort of cutoff here, this sort of critical stress that occurs. Okay, and that critical stress is related to what is known as a lattice resistance. Okay, and lattice resistance is basically the intrinsic resistance of any given crystal to have a dislocation moving. Okay, lattice resistance varies very strongly between different materials. This is an image, classic image taken from a 1996 paper that I've referenced here. And what you have here is a stress, the critical stress at which dislocations begin to move, normalized by the shear modulus. This is predicted by a theory, and this is observed from experiments. So, so this plot is supposed to be showing you that experiments and theories seem to agree pretty well. For our purposes, all I really wanted to bring your attention to here is just the values, right? So just the actual values of these lattice resistances. You'll see that they can span from a relatively small fraction of the shear modulus. So here at the lower end, you have 10 to the minus fifth of the shear modulus, up to a relatively high fraction of the shear modulus, right? So 10 to the minus 1. So 10 to the minus 1 of the shear modulus, you're talking about 10% of the shear modulus, right? So, in a typical, shear moduli actually vary a lot between different crystals, right? So copper has a shear modulus, it has two different moduli, right? Because it's a cubic material, so it has 3 independent elastic constants. But if you were to homogenize it and imagine it to be isotropic, its shear modulus would be around 80 GPa. At the same time, niobium, which is also a transition metal, and has a lot of similar properties to copper, crystal structure though, has a shear modulus of about 20 GPa, right? So you've got a factor of 4 difference in shear modulus. So shear moduli can differ quite a bit. But if you were to look at copper with a shear modulus of about 80, 1/10 of that would be 8 GPa, right? So, a tenth of the shear modulus is a very high stress. If your lattice resistance is that high, that means that your dislocations will never move, right? You'll never be able to apply a high enough stress to actually overcome the lattice resistance. When you look at the symbols here, you'll see that, for the most part, the things that, the materials that occur all the way up here are things like diamond, right? So diamond cubic materials, ceramics, silicates, right? So these SiO2, right? Quartz, things like that. Covalently bonded materials, things with extremely strong bonds, they have these extremely high lattice resistances. You can't move dislocations. You can't apply a high enough stress to move dislocations, because before you get to the level of stress needed to exceed the lattice resistance, you're likely to fracture the material, right? So diamonds, silicates, carbonaceous diamonds, silicates, many kinds of ceramics have such high lattice resistance that you can never actually move the dislocations. The intrinsic resistance of the lattice is too high. At the other end, right, these black circles that you see here are FCC metals, base center cubic metals. Those are the materials that tend to have the lowest lattice resistance. You also see some HCP metals, but that's different depending on which plane you're slipping on. So here they're talking about basal slip, which is a lot like slip in FCC metals. And in that case, the fraction of the shear modulus that you're talking about is 10 to the minus fifth, right? So at 10 to the minus fifth, you're talking about lattice resistances that are on the level of individual megapascals, or maybe a few megapascals. Extremely low lattice resistance, right? So low that they're really in the noise. For those of you who are, who do mechanical testing, you might recognize, NPA level stresses as being, a level of uncertainty that you might get from your load cell. Similarly, if you're doing atomistic simulations, you might recognize that, a slight, thermal misfit of a few degrees will give you NPA level stresses, right? So NPA level lattice resistances are as good as lattice resistances of 0. Right, so they're basically saying no resistance, right? So for FCC metals, you get dislocations moving at even the slightest applied resolved shear stresses, whereas at the other extreme, if you look at ceramics and other materials like that, you might not get dislocations moving at all, ever. In between, you have all kinds of intermediate cases. Perhaps the most interesting being the BCC metals. So these are here noted with the open circles. And BCC metals are an interesting intermediate case, right? They have a high enough lattice resistance that dislocations don't start moving immediately, but their lattice resistance is not so high that dislocations can't move at all, right? So in that case, in the case of BCC metals, there's this sort of intrinsic lattice resistance that that has to be overcome to make dislocations move. Okay. That lattice resistance is also related to the thermally activated processes that are actually responsible for dislocation motion once you can actually get a dislocation moving. So to begin going in the direction of explaining the mechanisms that are responsible for that, I just wanted to introduce to you two kinds of structures, imperfections, or you could say, that you can find on top of dislocations. So if I am dealing just with straight dislocations, right, then I just have a single line, featureless, nothing in particular to think about there. But of course, dislocations aren't always completely straight. Sometimes they can have some curvature in them, and when they have some curvature, that curvature can be accommodated, depending on the kind of dislocation you're looking at, by steps, basically by steps in the dislocation line. And those steps are of two types. They're either jogs or kinks. Jogs are steps that take the dislocation out of its glide plane. So you should think of this plane that I've drawn here as the glide plane. If I have a dislocation and a step takes the dislocation out of the glide plane as I'm showing you here, that's a jog. If I have a dislocation and there's a step in the dislocation, but it's still within the glide plane, that's a kink. Okay? Kinks are extremely important for how dislocations move when the lattice resistance is not super low, right? So for example, if you're looking at BCC materials, the motion of kinks is really the most important part of dislocation mobility. Why? Well, you can think of a straight dislocation as lying in a single, let's say, valley, a single trough in a potential energy landscape. So this figure that I'm showing you here on the right was taken from Hull and Bacon, that introductory to dislocation book that I told you about before. Let me think of each one of these dashed lines as a potential site where straight dislocation can sit. And as I guess it's the straight line. Sorry, the straight lines are the locations where dislocation can sit. And if I go from one straight line to another, those locations are going to be separated by little energy barriers, right? So there's valleys in this potential energy landscape, and then barriers, right? So as a dislocation moves from one solid line to the next solid line, it has to overcome one of these barriers. Okay. Now, of course, if I have a straight dislocation and I move it directly between one solid line and the other solid line, that means that I have to have the entire line overcoming that barrier all at once. Okay, and that's difficult, right? It's difficult to get enough energy to actually get the dislocation to overcome that barrier all at once. So what happens in reality is that the dislocation is never sitting in just one of these troughs, in one of these valleys, in a single valley, but rather it has a segment sitting in one valley, and then it has another segment sitting in another valley, and the region between those two segments, this little segment of the dislocation that goes between the two valleys, is a kink, right? And so here you have, a segment, and here you have another kink going to another segment in another valley, and here you have another kink going to another segment in another valley, and another kink, and so forth, right? So these are all kinks, joining segments of dislocations that are sitting in major valleys in this potential energy landscape. Okay, it is much easier for this dislocation to move by these kinks propagating, right? So if I have, for example, this kink right here. Let's say I have this kink, and this kink moves downward, right? If this kink moves downward, eventually it's going to come to this kink, and those two kinks will annihilate, and this entire segment of the dislocation that's sitting in this valley will be moved over to this valley, right? So this entire segment of the dislocation will move from here to here, but it will be entirely as a result of this kink moving down in this direction. Okay, so if you're talking about a material that has a relatively high lattice resistance, this motion of kinks is really what controls the mobility. Okay, so there are two sort of mechanisms, or two important steps in this kink mechanism that account for the rate of dislocation propagation. One of them is the motion of the kink itself, and the other one is the nucleation of kinks. Okay. Incidentally, let me just mention this. This potential energy landscape that's drawn here, the activation energy, this barrier, this energy barrier that you think that's separating the valleys, you can think of that as being representative of the lattice resistance. Okay, if this barrier is high, that means the lattice resistance is high. If that barrier is low, that means the lattice resistance is low. Okay, so whenever this barrier is super high, then the kinks are going to become much more important for the motion of the dislocations. Okay, so with that, let me move over to my notes. So I'm going to move to my notes now. Okay, so I told you all about kinks, all right, and I told you about how they move. And now, once you've thought about how they move, you have to think about the rates at which those kinks can move. So if you're going to write down the rates of kink mode, if I have a kink on a dislocation and I want to figure out the rate at which it moves, I can write that down. That rate is going to be proportional to an activation, to an Arrhenius factor, which has a certain activation energy in it, and I'll talk about that in a minute, and an attempt frequency mu. So for those of you, hopefully you've all taken kinetics at some point, so you realize that these kinds of expressions for rates are just a direct consequence of transition state theory, right? So the transition state theory tells us that the rates of thermally activated processes can be written down as an attempt frequency times a success rate, which is really an Arrhenius factor, okay? This Arrhenius factor, of course, has this thermal energy in it, kBT, right? So you've already seen this occurring in the last lecture. KBT is just a measure of the amount of thermal energy available per degree of freedom or per atom. And then you have an activation energy here, okay? And that activation energy consists of a kink migration energy, an intrinsic kink migration energy, delta M. And then it has this factor here, which is called the bias factor, okay? And that bias factor is a product of the resolved shear stress, tau, which I told you about before, and B cubed, which is an activation volume, right? So from the last lecture, you should remember the activation volume. And tau, the resolved shear stress, is as I've defined before. By the way, if you go back to the last lecture, you'll also see a derivation of how this expression comes about, right? So Amit actually did a derivation of how you can figure out the Helmholtz free energy of activation, and there is this component here that is related to the stress that's applied, right? So this tau is the applied stress, and the minus that you have here is showing you that the stress is applied in such a way as to make the transition more favorable, right? So this rate, I labeled it as R sub width, meaning that this is for kink motion with the applied resolved shear stress. And then I have another expression, R against, which is kink motion, thermally activated kink motion against the applied shear stress. That kink motion with the applied shear stress promotes shear stress, right? So the applied resolved shear stress, tau, right? So this tau is actually advancing the motion of the kink, and so it's reducing the activation energy for the kink to move. And if I were to look at the kink motion in the opposite direction, then this minus turns into a plus, which basically tells us that the applied resolved shear stress is opposing kink motion, right? So the applied shear stress gives us a bias for the kink to move in a particular direction. By the way, notice if tau is 0, right? If the resolved shear stress is 0, then the kink is as likely to move in either direction, right? So if the applied stress is resolved stress is 0, the kinks just undergo a random walk along the dislocation line. But if you apply a resolved shear stress, then you bias that random walk in a particular direction. Okay. So how do I compute a dislocation velocity from that? Well, I take the net rate, right? So I take the difference between the rate of kink motion with the applied shear stress, take away from that the rate of kink motion against the applied resolved shear stress. I plug in the expressions that I had before. I can simplify this expression using the formula for a hyperbolic sine, right? So if I use the formula for a hyperbolic sine, I get this expression. And then if I make the approximation, which is often used in mechanics of materials community, that we're dealing with relatively low stresses, then you can approximate 2 times the hyperbolic sine of this stuff inside as the resolved shear stress times the activation volume divided by kBt, the thermal energy. Okay. So whenever you want to make this approximation, you have to make sure that that the elastic energy associated with the applied resolved shear stress, which is this tau b cubed divided by 2, is small by comparison to the thermal energy. Okay, and unless you're at cryogenic temperatures where the thermal energy is quite small, if you're at room temperature or above, this will almost always hold true, right? Because elastic strain energies tend to be relatively small compared to thermal energies for the most part. Okay, so if I make this approximation and I plug it back into this formula for the rate of advance of kinks, then I can get this expression for the total kink rate, the rate of kink motion in the direction of the applied resolved shear stress, right? And you can see now that it's proportional to tau, right? And you can see that it's also dependent on temperature, right? So this is dependent on temperature. If I wanted to figure out the drift velocity, of course, remember that this rate that I've given you here is not like a ballistic motion, right? It's not like the kink, is always moving in that direction. This is basically a biased random walk. right? This kink is undergoing a random walk, but it's biased to go in a particular direction. And so it has a drift velocity. I'm not calling this a ballistic velocity, it's a drift velocity. That drift velocity is given simply by the Burger's vector of the dislocation times this rate of drift of the kink. And if I know the density of kinks, basically if I know the spacing between kinks on the dislocation, let's assume that that spacing is L, right? If I assume that the kink spacing is L, if I know that spacing, then I can compute from the drift velocity of the kinks the velocity of the dislocation, right? A dislocation segment of length L will move ahead of Burger's vector when a single kink moves over the distance L, right? So the dislocation moves ahead by one Burger's vector B when the kink moves by a distance L, right? So I can compute the dislocation velocity V from the kink velocity V sub k as B times V sub k divided by L, right? So that's my dislocation velocity due to kink motion, right? Just one more thing to talk about here. And this is, by the way, this is just putting it all together, right? So if you take this expression here that I have for R, plug it into the expression for V sub k, plug the expression for V sub k for E, plug it all together, I get this whole thing. I can group terms. I can take this Arrhenius term here, combine it with this new term and the B squared term, and I get basically a one-dimensional kink diffusivity. Right? So that's one way to think about this, is that the velocity is proportional to the kink diffusivity, and then this combination of terms here, right? Tau times B cubed, which is the activation volume, and then L, which is the spacing between kinks. Okay? So the one thing that I have left for you left to tell you now is, how do I get L? How do I get the spacing between kinks? Okay? And the answer is, it depends on the stress. Okay, the value of L depends on the stress that's applied. So in the limit where the stress is low, let me back up a little bit. Kinks are defects on dislocations, you could say, right? They're isolated spots on top of a dislocation. Dislocations are line defects. So if I were to think of atomic scale kinks on top of a line defect, a dislocation, those kinks are like point defects, right? Those kinks are not line defects, they're not area defects, they're like point defects. And whenever you're dealing with point defects, you have you are always going to be dealing with the possibility of having a thermodynamic equilibrium concentration of those defects. And indeed, you can compute the thermodynamic equilibrium concentration of kinks on a dislocation line. And this is the expression for that. When the stress is not too high, the spacing between kinks, 1 over L, is given just by this formula here, which is giving you the thermodynamic equilibrium concentration of kinks. This formula is 1 over the Burger's vector times a Boltzmann factor, and that Boltzmann factor has the thermal energy, kBT, and a kink formation energy, delta E F sub k. Okay? Notice that I'm calling this factor here a Boltzmann factor, and I was calling this factor here an Arrhenius factor. And the reason why I was calling this an Arrhenius factor is because it has to do with rates. I'm calling this one a Boltzmann factor because it has to do with thermodynamic equilibrium concentrations. Okay? So kinks have formation energies, just like point defects. You can calculate the equilibrium concentration of kinks from that formation energy, and it's just a very similar expression to the vacancy concentration. So if you're at relatively low stress, you have a thermodynamic equilibrium concentration of kinks. You can plug the expression for 1 over L into your expression for dislocation velocity, and there you have it. Okay? So this is the expression for dislocation velocity as a result of kink motion at relatively low stress. Now, what happens at higher stresses? Well, what happens at higher stresses is that the kinks start to move so fast that they get swept off of the dislocation before they can reestablish a thermodynamic equilibrium concentration again. And in that situation, the mechanism of kink-mediated dislocation motion changes. it changes from the thermal activation of individual kinks to the thermally activated formation of kink pairs. Okay, so let me go back to this picture that I had above here. Right, so I was telling you before about, if you have this kink moving towards this kink, right, then they're going to annihilate, and you'll get a single line of dislocation here. Okay, if I'm starting out with a straight line of dislocation, and I want to create a kink pair, right, then I'm talking about a segment of dislocation moving over to a nearby valley in the energy landscape. And for that to happen, it has to simultaneously form two kinks. Okay? The activation energy for that to happen is 2 times the kink formation energy, at least. Okay? 2 times the kink formation energy plus probably some other, activation energy associated with the activation process itself. So the activation energy to form a kink pair is much higher than the activation energy for a kink to move. So typically what happens is at low stress, the kinks basically maintain a thermal equilibrium concentration on the vacancy. When stresses get higher, those kinks get swept out, and then the progress of the dislocation is no longer governed by the motion of the kinks, but rather by the thermal activation of the kinks, thermally activated formation of the kinks, and the activation energy then changes. I think that I have an expression somewhere in here for the activation energy of kink formation, but I'm not going to go over it. Okay. Once the applied stress gets high enough, even the formation of kink pairs becomes governed by stress rather than by thermal activation. So to describe the formation energy of kink pairs, there are phenomenological expressions that have been developed, such as this one. Okay, this is an expression that I took out of Argon's book, Strengthening Mechanisms in Crystal Plasticity. It basically tells you that the Gibbs free energy to form a kink pair is equal to the enthalpy at 0 applied resolved stress times this factor, which is basically 1 minus a ratio of the resolved shear stress by a certain tau max squared. And really all that this is telling you is that when the resolved stress approaches some magic number, tau max, the Gibbs free energy to activate kink pair formation goes to 0. What does that mean? That means that you no longer need thermal activation to create kink pairs. You can do it simply by having a sufficiently high resolved shear stress, tau, right? That resolved shear stress, tau max, is sometimes known as the mechanical threshold, right? So there's a threshold stress, tau max, beyond which thermal activation is no longer required. The activation is entirely mechanical. There's no simple analytical expression that I know of for tau max. These things are usually determined by calculating them from atomistic calculations or by backing them out from experiments, okay? But basically, once you exceed this tau max, you no longer are in any need of thermal activation to move dislocations, right? And at that point, you move out of that regime that I told you about before, where the motion is thermally activated, to a motion to a regime where the motion is no longer temperature dependent. Okay. I'm running out of time, so I'm going to go through the rest of this, fairly quickly. And for those of you who are interested in more details, I will be sending these notes out, so you're welcome to look at that. Once you exceed that mechanical threshold, there are 2 phenomena that take place. One is that your dislocation begins to move in a manner that you can think of as being ballistic, right? So rather than thinking of a dislocation as a configuration whose motion is governed by thermally activated kinetics, the approach has been to think of the dislocation as moving under the influence of Newton's laws, so ballistically, F equals ma. Rather than thinking of the resolved shear stress as being a thermodynamic driving force, you think of the resolved shear stress as being an actual Newtonian force leading to an acceleration of the dislocation. And of course, forces lead to accelerations, and we know that dislocations acquire specific characteristic velocities at any given applied resolved shear stress. And the only way that's possible is if there's some drag, right? So for a dislocation to reach a certain terminal velocity under an applied resolved shear stress, there have to be mechanisms that dissipate energy from it, and those are called drag mechanisms. And so there are many different drag mechanisms that have been proposed. And so I'm just going to sort of mention a couple of them without really going into detail. One of them is known as phonon drag. And phonon drag is probably one of the sort of most typically cited reasons for dislocation velocities reaching a terminal value above the mechanical threshold. And there are a couple of different mechanisms by which phonons can exert drag. One of them is that they can radiate energy from the dislocation if the dislocation flutters, right? So if it doesn't remain completely straight, but sort of flutters a little bit as it moves, that can emit sound waves that carry away energy, right? Which basically are a form of drag. Another one is that phonons can interact differently with the dislocation core if the elastic constants near the dislocation core are a little bit different than the elastic constants away from the dislocation core. That's known as an inhomogeneity interaction. And whenever you have that difference in elastic constants, the phonons can scatter. And whenever you get phonon scattering, that again is a way of transferring energy away from the dislocations. And finally, as the dislocation moves, it's actually creating stress fields around itself, stress fields and strain fields. And so there's going to be atoms that are going to be undergoing transient, non-uniform stresses in the vicinity of a moving dislocation. And that dissipates energy as well, especially if there's any sort of viscoelasticity in the material. So I'm not going to go more into that. There's a little bit more information here. It tells you some numerical expressions for phonon drag. These numerical expressions are entirely phenomenological. They've been derived from measurements of dislocation velocity, such as the one that I told you about. And instead, what I'll do is, just with my last minute or two before wrapping up this talk, I wanted to point out this idea of relativistic effects. Okay, so people have determined expressions for stress fields of moving dislocations. So this is just one example. This is a stress field of a moving screw dislocation. Okay, you're probably used to seeing stress fields of static dislocations, right? And this, expression that I'm showing you here is actually quite similar to that. The only difference is that it has this term gamma, and it has these V's here, right? So the V is the velocity of dislocations, of the dislocation, and the gamma is a factor which is written as written here, right? So square root of 1 minus V squared, the velocity of the dislocation, divided by C sub t squared. C sub t is the transverse sound speed. So basically just sheer sound speed, shear wave speed, okay? Where do these formulas come from? Well, they come from just linear elasticity, right? So if you were to solve the linear elasticity equations for a moving dislocation, right, you can do that, within the framework of linear elasticity. There's no special theory that you have to assume to get these equations. This is just done by linear elasticity. You get these expressions, but in these expressions you have these terms gamma, right? And these gamma terms, for those of you who are physicists, you will recognize this as being quite analogous to what shows up in Einstein's theory of special relativity, right? Einstein's theory of special relativity also has these kinds of gamma terms. And these gamma terms make it so that these equations for the stresses become singular, have singular behavior when V approaches the transverse sound speed. Right? So when the velocity of the dislocation approaches C sub t, gamma becomes 0. You can see that that the stresses, that the numerator in those stresses is going to become 0. And on the bottom, you're going to get the y dependence going away entirely. And you're going to get a very sort of singular stress field that has no y dependence, only the x dependence. And then it has, and then there are other, sort of consequences that come out of this. You can use these stress fields to compute the energies of a moving dislocation as related to an energy of a static dislocation, right? Computing dislocation energy is very simple, right? You can just use the equations of linear elasticity to figure out the strain energy, right? The elastic strain energy. And it turns out that if you compute the elastic strain energy of a moving dislocation, it can be written as the elastic energy of a static dislocation divided by gamma, right? And again, this is just, I'm just talking about algebra, right? So you just, integrate these stress fields and you get this energy for a moving dislocation. And this gamma is this sort of weird relativistic factor that looks a lot like Einstein's theory of relativity. And you can see that as v approaches the transverse sound speed, gamma goes to 0, and the energy of the moving dislocation goes to infinity. Okay? Again, this is an analogy to what happens in Einstein's theory of relativity. If you try to accelerate an object to close to the speed of light, its mass will increase so as to keep you from ever crossing the speed of light. Here, there's an analogous process occurring. The elastic energy of the dislocation is predicted by linear elasticity to increase without bound as you approach the transverse sound speed, such that you can never push the dislocation above the transverse sound speed. Right? So this is sort of like a relativistic limit. And it causes the dislocation velocity to bend over an asymptote to the transverse sound speed as you continue to increase the applied resolved shear stress, right? So that's where we get this bending over of the dislocation velocity occurring. Okay, there's a couple of other things here that I talk about which allow you to define a dislocation mass, and you can sort of see how you can extend this relativistic analogy to mass as well. But I'm not going to go through that. I think those of you who are interested in it, again, I invite you to read my notes when I send those to you. So I'm going to stop sharing this at this point. And since we only have 10 minutes, take any questions that you might have. Oh, maybe before that, one last thing. I am giving you some problems. Right, so I'm going to give you some problems to work on. Okay, so one of them I already told you about, and that is to work on this Burgers vector. This is the other one. Consider a jog on a screw dislocation as drawn below. Show that if the dislocation is to move in the x direction, the jog must climb. Right. So you should be able to show, based on what I told you about glide planes and how you determine glide planes from Burgers vectors and line directions, that this dislocation can only move if the jog climbs. Okay. And those are the two problems I'm going to do. I'm going to skip this third problem because I never got a chance to get to the material that I have in problem number 3. So with that, I'm happy to take your questions.
Thank you, Mike. We have a few minutes today, and we will have time on Thursday to have more questions.
Absolutely.
There's one question from Tadung. Can you explain more about the movement of dislocation jog? Is it correct that because dislocation jog is not happen in slip lane, so it does not contribute to shear deformation? Also, jog motion is not related to thermal activation, or is jog motion related to thermal activation?
Yeah, so part of that, so you're anticipating the solution to problem number 2 that I mentioned. I guess I'll say it. You can still work the problem after I tell you, but basically, for a jog to move, at least when you have a jog on an edge dislocation, that requires mass transport, right? So a jog can only move if atoms are being transported to or away from the jog, and you can figure that out really easily by showing that the motion of the jog is not in the glide plane. right? So basically, as soon as you can show that the jog doesn't move in the glide plane of the dislocation, you know that its motion must be non-conservative, right? So therefore, the rate at which it moves depends on the rate of diffusion, okay? And that is definitely thermally activated. That is, in fact, impossible to activate without thermal activation. Well, if you have a high enough stress, you can actually drag a jog. And in that situation, what's going to happen is as the jog gets dragged, it leaves behind point defects. So yeah, I guess you can move a dislocation without thermal activation, but at the cost of creating defects.
Okay, I don't see any other questions right now, but I'm sure there will be more as people read through your notes. And then we can reconvene on Thursday to discuss the homework solutions and have more Q&A.
Sounds
So
good.
thank you very much for your lecture.
Thank you, everybody.
Thank you, everybody, for staying late.
Bye-bye.
Bye.